Well, what I thought would be useful today, I wanted to start in a very elementary way. This will be stuff you've seen, but then I want to move on and talk about, first talk about the ideal Bose gas. And there are obviously two important cases, the one in a box which is uniform, translationally invariant with periodic boundary conditions, but the other one is a harmonic trap, and you can generalize the harmonic trap to anharmonic traps in various ways, although I won't go into that. And then I want to talk about the effective interactions in the uniform case, which is the Bogusubov theory, and you've probably seen this, but it's worth going through the details because it's a very elegant and remarkable set of results. And that's probably about as far as I'll get today. Probably next time I will use the Bogusubov theory to calculate S of Q and omega in a non-trivial example. So you can see how you get these delta functions associated with the quasi-particles, and once you've got S of Q and omega, then you can calculate S of Q just by integrating overall frequency. And because I'm going to do this at finite temperature, you get all these nice finite temperature results, and you can also verify that the S of Q that you write down satisfies this detailed balance condition, and it satisfies the F sum rule. So as I say, these are very non-trivial conditions, and the fact that it satisfies all these different conditions is actually pretty remarkable. So let me start with a box. In this case, we have a couple of basic energies. We have the number density n, which is n over v, and I can call this 1 over L cubed. So L would be the interparticle spacing, apart from factors, however you want to define it. And then whenever you can think of each particle in a little container surrounded by all its neighbors. And the size of this container is of order L. And so the zero-point energy associated with this confinement, if you have a particle in a spherical box, the zero-point energy is of order h bar squared over m L squared. That's just from basic quantum mechanics. So you can write this as h bar squared over m times n to the 2/3. And this is the basic quantum energy in all these problems. And then we want to compare this with the thermal energy, which is kBT. And at high temperatures, this is very large, this is very small, and the system is basically classical. But as you increase the density or lower the temperature, at some point you get E thermal is of order the zero-point energy. And when that happens, you then say that Kb, this defines the transition temperature, h bar squared n to the 2/3 over m. And this is the basic onset of quantum degeneracy in almost any quantum system where you don't have another parameter such as the size of the trap or something like that. Now, there's a completely different but analogous way. This is a condensed matter point of view. This is what I would have always taught in my classes. But you know there's also the optics or quantum optics point of view where you say, you say p squared over 2m. You set that equal to kBT. This defines a quantity P thermal, P sub T if you like, which is of order m kB T with a square root. This is just the thermal momentum associated with a particle with particles in equilibrium at that characteristic temperature. And then you set lambda thermal from the de Broglie relation as h over pt, and this is h or h bar. You can put factors of 2 in how you want, or pi's. It's h bar over the square root of m kBT. And this is the de Broglie wavelength associated with a particle in thermal equilibrium. And if h goes to 0, this goes to 0. Or if t goes to infinity, this obviously goes to 0. So either in the classical, the high temperature limit, or the quantum limit, the thermal, in the classical limit or the high temperature limit, the thermal wavelength goes to 0. And now again, you want to compare lambda thermal. How does it compare to the interparticle spacing? and I've seen this drawing in many things that Ketterle's done, but it's very common. If you have two particles separated by a distance L, and lambda thermal is much less than L, then you get a picture like this, and these are the quantum diffraction waves associated with the characteristic thermal wavelength lambda. And so, and this is the classical limit, because in the classical limit, the diffraction effects are small, and in the limit where lambda goes to 0, it's just like using geometric optics instead of going through the tedium of trying to solve Maxwell's equations or some scalar version of Maxwell's equations to study what happens when you have light passing through some aperture. But as you make L smaller, or you lower the temperature, if you make L smaller, you're making the density bigger, or you lower the temperature, eventually you get to a regime where lambda thermal is of order L. And when that happens, then you get these diffraction patterns overlap dramatically, and so the quantum waves know that the other particles are nearby, and so you get this interference effects start to play a very important role. And this is the onset of quantum degeneracy. In the language you're probably used to, you write this instead of this way. You say n lambda thermal cubed is of order 1, and that's the onset of quantum degeneracy. And this is called the phase space density. But if you play games with this, you'll see this condition is exactly the same as this condition, apart from factors, whatever numerical factors you want to put in. So I presume this is something that you've heard. What's interesting, this applies to fermions as well as bosons. There's nothing about the statistics. So for electrons in metal, n is the order of 10 to the 22 per cubic centimeter. And if you work out Tc, you put the mass of an electron in, you get Tc is of order 10 to the 4th. I mean, it's usually called the Fermi temperature for metals, but it applies for neutron matter. It applies for white dwarf matter. It applies for any kind of condensed Fermi systems. Now, if you take helium, the mass of a helium is approximately 10 to the 4 times the mass of an electron. And so, very conveniently, Tc for helium, either helium-3 or helium-4, is of order 1 Kelvin. And the actual temperature for helium-4 is 2 point something. And you don't get a phase transition in helium-3. You get a crossover between the classical regime and the quantum regime, just the same way. You don't get a phase transition in metals when you cool it down. In fact, of course, you never get metals in the classical regime, because any metal at this temperature or higher will be not a metal anymore. So the metals are always degenerate, and it turns out that white dwarf stars and neutron stars, in all practical cases, there's a factor of, the temperature is roughly a factor of 10 less or 100 less than the typical Fermi temperature. So they're very quantum degenerate. Now, I'm just going to focus on the bosons, but it's interesting that the same kind of idea of quantum degeneracy works equally well when you talk about fermions. The details are different, of course, because you don't have bosons like to be together, and fermions like to be separate because of the exclusion principle. And that simple change makes a world of difference, and you can see that in the comparison of helium-3 and helium-4. Helium-3 and helium-4 have exactly the same electronic structure, and all you do is take one neutron out of the alpha particle and you get a helium-3 atom. But the behavior is completely different. And as I was talking to some people yesterday, Landau didn't really believe that quantum statistics had anything to do with superfluidity. He was confident, I think, until the experiments were done, that helium-3 would have a superfluid transition just like helium-4, because he thought it came out of some kind of quantum hydrodynamics. And that's where the name Rotan ultimately came from, because of there were states that had zero angular momentum, and there were ladders of states that had finite angular momentum, and there's a gap between them, and that was the Rotan gap. That turned out to be wrong, but it certainly, he also predicted second sound in that same paper, which was pretty amazing, and that was seen. So, I mean, it's not a crazy paper, he pushed it way beyond where it should have. Okay, now I want to be a little more quantitative. So suppose I have a complete set of, I have some Hamiltonian, and I have some set of single particle states J and some energy levels epsilon J. And I want to do the statistical mechanics of a set of particles in this system. And what I'm going to do is, I mean, again, you've seen this before. We want to take the grand canonical ensemble at temperature T and chemical potential mu. And that's the easiest way to think about doing quantum systems as you lower the temperature. So we have a complete set of single particle energies. The beauty of this approach is you almost, for most purposes, you never need the single particle wave functions, which are rather intricate in many cases. Now, we know that the mean occupation of a state J under these conditions is what I'll call F of epsilon J, where F in general is 1 over e to the beta epsilon minus mu minus 1. And the minus 1 here makes it a boson. So this is the mean occupation of this particular state when you're at temperature T, which is 1 over beta, if you like, apart from Kb, and mu, which appears here explicitly. Okay? And then if you just grind through the grand canonical ensemble, the total number of particles, n, is a function of T and mu, is sum on J nj, or if you like, sum on J F of epsilon J. And the energy, the internal energy as a function of T and mu, is sum on J epsilon J nj, or sum on J epsilon J F epsilon J. Okay? Now, this is a little awkward because we don't normally think of controlling the chemical potential. Formally, you invert and get mu as a function of T and n, but you rarely can do that analytically. You can surely do it numerically. And then if you substitute this back into here, what you would end up with is E as a function of T and n, which is probably what you're more used to thinking about. So it's a little intricate, but that's just the way it is. And it's convenient to introduce what I'll call the density of states, G of epsilon, the sum of delta functions, one-dimensional delta functions, epsilon minus epsilon j. Okay? And with that notation, I can write n of T and mu integral d epsilon, G of epsilon, F of epsilon, and E of T and mu is integral d epsilon, G of epsilon, epsilon, F of epsilon. Okay? And if you just substitute this sum of delta functions in here and do the integrals, you reproduce these results immediately. Now, this is a little weird because you're dealing with a sum of, typically an infinite sum of singular functions, but at least in practice, you can approximate the sum by integrals. And then the integral over the delta function, you have, say, a three-dimensional integral in some sense. You have one constraint, so you can then do the integrals, and I'll give you the answers for the box and the harmonic oscillator. You may never have done them, but they're not hard. Now, in the classical limit, it generally happens that mu goes to minus infinity, or mu over kBt goes to minus infinity. So if mu is large and negative, this is perfectly well defined. What gets to be a problem is if epsilon is equal to mu, because then e to the 0 is 1 and you got a 0 in the denominator. And since you're summing over all states, we insist that mu has got to be less than epsilon 0, the ground state energy of whatever system you're looking at. And the criterion for the onset of Bose condensation, if it's going to happen, is that mu equals epsilon 0. And at that point, then this becomes singular. And then the issue of how the density of states behave for epsilon equals mu becomes crucial. And that's why it's important to be able to evaluate these things. So, because otherwise you don't know whether you're going to get a BEC or not. And there are many cases where you do, but there are also many cases where you don't. So we can identify the criterion for the onset of Bose condensation. If we imagine we've done this inversion, mu at Tc and n is equal to epsilon 0. This is the criterion for, this is how you determine Tc. Now, you really do it from this expression, or this expression, because what we say is that n, which is the total number of particles, will be, it's a function of Tc, and now I set mu equals epsilon 0, and I get the integral, this runs from epsilon 0 to infinity, d epsilon g of epsilon divided by e to the beta epsilon minus epsilon 0 minus 1. And when at the lower limit, when epsilon's equal to epsilon 0, the denominator vanishes. The only way this integral can converge is if g of epsilon also vanishes. So basically, one way of thinking about it is to say the criterion for Bose condensation is that g of epsilon vanishes at epsilon equals epsilon 0. When the density of states at the ground at the lowest level has to be 0. And now I need to be specific. So let's look at the case of a box, which is certainly familiar. But so I'm going to leave these criteria, but the rest of this I'm going to now erase. Okay, so let's take a box, 3D box. Take a cube on size L, and V is L cubed. And I'm going to take periodic boundary conditions, which is a particular choice of psi. And so instead of J, I'm going to use the wave number K, which is 2 pi over L times a triplet of integers, n1, n2, n3. And n1, n2, and n3 can be any integers, positive, negative, or 0. The alternative is to use hard wall boundary conditions, but that's much less physical. So I don't know why books ever use the hard wall boundary conditions, because it doesn't describe any real system. It may describe electrons in metals, but it certainly doesn't describe a Bose gas. Because the ground state of this system is 0, 0, 0 is a uniform constant, which is what you would expect for particles in a box. When you have condensation in the zero momentum state, you expect to be uniform, not a product of sine waves. The product of sine waves is very non-perturbative, because if you apply an arbitrarily small interaction, it'll suddenly spread out. And so it's better to start with a thing that's uniform before you start, then you don't need to have this sort of discontinuous perturbation when you turn on a weak repulsive potential. So the wave function here is psi sub k of r. It's 1 over the square root of v, e to the I k dot r. And this is periodic if you increase r by L in any direction x, y, or z. And so this is manifestly periodic. It's a function of r, but we're labeling it with k. This is like psi sub j. Okay? And now we have to calculate the density of states. G of epsilon equals the integral d3k. You get a factor of 2 pi cubed, and there's a factor of the volume. That just comes from transforming this sum over states to an integral. And then you get a delta function that tells me that epsilon has to be equal to h bar squared k squared over twice the mass. And this is an integral that's reasonably straightforward to do. The trick is, it depends only on k squared, so you use spherical polar coordinates. And I could show you how to do it, but I'm not going to do it here. And you get the answer V over 4 pi squared, 2m over h bar squared to the 3 halves, the square root of epsilon. And as we hope, this goes to 0 when epsilon goes to 0. So in 3 dimensions, we do get a Bose condensation because this criterion makes sense. Okay? So let's fix n. I fixed the number on the left-hand side, and then I imagine lowering the temperature. And as I lower the temperature, originally mu classical, and I'm not going to prove this, but you can work this out, is kBT times the log of n over v lambda thermal cubed, which of course is just the log of the phase space density. Now at classical limit, the phase space density is very small. The log of a very small number is negative. And so this actually is large and negative. Now as you increase mu from minus infinity, the integral n of t in mu, which is integral 0 to infinity d epsilon g of epsilon over f over e to the beta epsilon minus mu minus 1. As you increase mu from minus infinity, in order to keep this equality satisfied, you have to lower the temperature, because you have a fixed number over here, say Avogadro's number. And so you have to fine-tune the temperature and the chemical potential to keep this value fixed. And when you get to mu, in this case, the ground state has 0 energy, 0, 0, 0 here. So when mu equals 0, this integral here now is going to run from 0 to infinity. And that determines an implicit equation for Tc that n of Tc and 0 is integral 0 to infinity d epsilon g of epsilon times e to the beta epsilon minus 1. And this is an integral you can do analytically, at least in terms of tabulated functions. And you put in this, then you put in all these factors, and what at the end of the day you get kb Tc is 3.3 h bar squared n to the 2/3 over m, which is just what we'd argued that this is the characteristic size of the Tc, and you just get a numerical factor. And if you put in the mass of the helium atom, you actually get about, I can't remember, something like 3 degrees. So it's, I mean, I think that's pretty impressive that that gives you an idea of why the thing makes sense. Now for T less than Tc, what happens is that mu can't get any bigger. Mu can't get positive because this integral is going to have a disaster. And so what you have to do is say, you start putting a finite fraction of the particles into the k equals 0 state, and then you use this integral to find the particles out of the condensate. You really are doing a sum here, if you remember. And since g of epsilon goes to 0, the density of states excludes the k equals 0 state from this integral in some sense. And so at the end of the day, what you get is, for t less than Tc, you find that n prime, the number of particles outside the condensate over n, goes like T over Tc to the 3/2 power. So at 0 temperature, all the particles are in the condensate. At Tc, none of the particles are in the condensate. They're all out of the condensate. And this gives you the behavior n0 over n is 1 minus this, and it looks like that. So you say that n0 plus n prime is equal to the total number n. Now, I mean, people worry about this mathematically, but it's okay. So I'm not going to worry about it. You can also use this formula I had a formula for the energy, and you can find the energy, and from the energy you can get the heat capacity. And what's interesting is the heat capacity, CV over N, is 1.93 T over Tc to the 3 halves if T is less than Tc. So you get this curve of CV over N versus T, and it looks like this. And this is Tc. And the classical limit is 3 halves. So a lot of work is needed to show that this comes down like that. So there's a discontinuity in the heat capacity. It's a subtle thing. It's not a divergence, but it's a discontinuity. Now, just for fun, you can do other dimensions, d equals 2 or d equals 1, and what you find is that g of epsilon goes like epsilon to the d over 2 minus 1. And I guess that's something that you worked on with Dan Kleppner. So at d equals 2, this is a constant. And so at d equals 2, you don't get, this has no solution because this is finite and this goes to 0 at epsilon equals 0. Now, it's actually rather subtle, and it's a question of order of limits. People like to think about turning the dial for the dimension, and it's a question of how you vary the temperature and the number of atoms and the dimension. And it's, I mean, I think it's well understood. The issue is it's a log divergence. And so the numbers of particles you have to be thinking about is huge if you're going to try to see any of these divergent properties in practice. Okay? So it's not clear what you mean by the thermodynamic limit. Actually, in the 2D case for an ideal Bose gas, you can do it analytically. There's a trick. You can do the integral analytically, and then you can actually, I mean, I guess you wrote it down yesterday. It has the, Chris wrote it down. It has mu is given explicitly in terms of an exponential or something, and you can work it out. You can invert it, but it's because you can do the integral. You end up in 2 dimensions. Well, if you just put g of epsilon as a constant, you can actually do this integral, and it's log divergent. Again, I haven't gone through the details in quite a while, but you can look it up. Now, the other important example is a trap, and this is, I just thought I'd focus on the isotropic trap because that illustrates all the points. And you can do it all in the same formalism, but you have to work a little harder to calculate the density of states. And again, I'm not going to try to do it. I can talk to people about it if you're interested. So just for fun, let me take a spherical trap, simplest 1/2 m omega squared r squared, just to, it just makes the writing a little simpler. And this is a familiar quantum mechanical problem. The energy levels are specified by nx, ny, and z. And these run from 0 up to infinity, not negative, as you know. And the energy epsilon nx, ny, and z is just h bar omega, the integer nx plus the integer ny plus the integer nz plus 3 halves. Okay? And psi j is a product of 3 Gaussians. And the typical size is the oscillator length d, which is equal to the square root of h bar over m omega. Okay? And again, I'm sure you know all this. Now, how can we estimate Tc? That's not so simple because you don't have an intrinsic size for the trap. It's not like a box where you have a volume and a characteristic dimension. And if you keep adding more and more particles, they just creep up and fill wider and wider dimensions. So it takes some thought. The first thing you do is say, well, let's use d, but that doesn't work. And so you have to come back and remember Boltzmann. who says the relative probability of a state with particular energy goes like e to the minus beta e, and particularly with the trap, we say the relative distribution, the probability as a function of r, goes like e to the minus beta times the trap potential as a function of r. And this has a very nice form because the quadratic, this goes like e to the minus m omega squared r squared over 2 kBt. So the nice thing here is this is a Gaussian. So the density of particles in a trap in the classical limit is just a Gaussian distribution. And you can read off the characteristic, call this e to the minus r squared over rt squared. And so rt, apart from factors of 2, goes like kBt over m omega squared. And if you can play games with this, one thing that's interesting is to write it in the form d squared over kBt over h bar omega. So in the classical limit, kt is much bigger than h bar omega, so d squared is much smaller than rt squared. Okay? And now we can use this to estimate. Now I'm going to use rt as the characteristic length. So what I'm going to say is kbtc is now of order h bar squared over m times rt squared. Because this is just like this h bar squared n to the 2/3 over m. And in a box, I just use the interparticle spacing, 1 over the interparticle spacing squared. But here there isn't, because the density changes, it's not so simple, and this is a nice simple estimate. Now, if you use this formalism, you see that you just get h bar omega squared n to the 2/3 over kbtc. Because I need, let's see, I need the density, I need a factor of n to the 2/3 here, because this is the macroscopic size. And now you see you get Tc here, and you can do some simple algebra, and you get kbTc is of order h bar omega n to the 1/3. So this is a hand-waving argument that gives you this n to the 1/3, whereas in the other case you get a different power of n. And so you get these very familiar pictures that the thermal cloud looks like this with a characteristic size RT. This is for T bigger than Tc. And then if you cool it down, you still get a thermal cloud, but you get this very narrow peak occurring on top of it, which has a characteristic size D. And these are all the famous pictures that you've seen many, many times. And if you put in some numbers, just typical numbers, what you get is that N is like 10 to the 6th atoms. D is of order a few microns. Omega over 2 pi is typically of order a few 100 hertz. Tc is, say, half microkelvin. And at the onset, R sub Tc over D is of order n to the 1/6, which is of order 10 typically. So these are the, that's where you get this picture from. There's a factor of 10 difference between this size and the narrow condensate peak, typically. You can adjust this by varying the numbers. Now I want to come back and do a more careful treatment where I try to be a little less hand-wavy. But I think it's worth doing. It's nice to see that you can just by back of the envelope estimates, you can understand most of what's going on here. So the energy of the oscillator in x and y and z, you need the triplet, is this h bar omega in x plus ny plus nz plus 3/2, where the 3/2 is the 0-point energy. And now I want to calculate the density of states, g of epsilon, and I'm going to approximate the sum by an integral. And because basically you write this as sum on nx, ny, and z of this delta function. But as you do the sums, n increases by 1. And if the energy is large compared to just h bar omega times 3/2, this doesn't change very much. And so I can approximate this. I can put in a factor of delta in x, which is 1, because you go from n to n plus 1 for each x, y, and z. And so using this trick, this looks like a Riemann integral, Riemann approximation to an integral. And so you approximate this by integral 0 to infinity dnx, dny, dnz, the delta function that says that the energy has got to be equal to h bar omega nx plus ny plus nz plus 3/2 if you want to worry about the 0-point energy. Okay? Now, this is less trivial, because the Raud region of n is non-negative for all the values. And this tells you that the sum of the three integers has to be a constant. So you basically take the corner of a room like this, and then you have a plane, and you have to figure out what is the condition, what's the number of states that lie on the plane, because the delta function, you can't go to spherical polar coordinates because it's not a sum of n squared, which is a distance in three-dimensional space. So you really have to do this integral. And at the end of the day, you get a very simple answer. G of epsilon is approximately epsilon squared over 2 h bar cubed omega cubed. G of epsilon obviously has to have the dimensions of 1 over an energy, because the delta function has the dimensions of the inverse of its argument. So you get epsilon squared over this cubed, and so you do get the right dimensions for this. And what you find if you go back and do it, I'm not going to do it, is KB TC is something like 0.94 h bar omega n to the 1/3. So it has exactly the same thing that you guessed, but now you get the right answer. And for t less than TC, you get macroscopic occupation of psi 0, which goes like e to the minus r squared over 2d squared. So this is and the coefficient is n naught of t. So this is the number of particles in this state. And so you get a macroscopic occupation, and at 0 temperature, all the particles are in this condensate, if it's an ideal gas. And what you find, it's not hard, you just do the integrals out. N of 0 of t divided by n is now 1 minus t over tc cubed. The cube comes out just because of the way the numbers come out. In the box, you get 3/2. So this is a steeper function. And what you find is the heat capacity divided by the number is something like 10.8. There's a factor of KB times T over TC cubed. So at the transition temperature, the heat capacity is actually very, very large. By a fact, you normally would think of heat capacities as being of order KB, maybe times 3/2 or something, but the fact that it's 10 instead of 1, I don't have an explanation for it, but it just does that. And the other thing that's interesting, back on your work, is that if you take a general D, you get that G of epsilon in the harmonic trap goes like epsilon to the d minus 1. So if d is 3, you get this result. If d is 2, you get 1. So the 2D Bose gas in a box, in a trap, for most purposes is reasonably okay, because you do get a condensate. You get a real condensate, as opposed to the box where you don't get a real condensate. Now d equals 1, one-dimensional Bose gas in a trap is, then you get a constant density of states, and that's kind of like the two-dimensional box Bose gas. Okay? And so, I mean, this is stuff that I think you've heard before, but it sets the stage for things I'd like to do now. And the first thing that you want to know is, how do you put in the interactions? Now, putting the interactions in for a box is reasonably straightforward. It's not trivial. It's very interesting. It's very important. In fact, it's probably the most, I would have said, I don't know what date to put at the beginning, but until the BCS theory, the Bogoliubov result was probably the most important result in many body physics. Maybe that and the electron gas. But this was 1947. So it's long before the electron gas was considered except in the lowest order. And you had divergences in the electron gas. You had divergences in the loop Bose gas. And they're very subtle. They're very subtle and hard to solve. And I've heard C.N. Yang several times. He worked on this in the late 50s. He was very dismissive of Bogoliubov. He said he didn't think Bogoliubov really understood it. I think that's crazy. But I'm always amazed at the arrogance of people who, with Nobel Prizes, who aren't willing to acknowledge other people's work. There are a lot of people like that out there.
Yukalov was the student of Bogoliubov.
Well, I gather he was a difficult person. I never met him, obviously. Anyway, I want to talk about interacting systems, but I can't do it for the trap. We'll talk about that next time, but it's much more complicated than the Bogoliubov theory of a box. But the Bogoliubov theory of box is pretty subtle, and it took people, I don't know how long, to really understand it and appreciate it. So we have, in a box, we have the interparticle spacing, n to the minus 1/3. And for an ideal gas, that's all you've got in the temperature. I'm going to now set t equals 0. But I'm going to assume that there is an S-wave scattering length, A, or let me call it just G. I'm going to assume that there is an interaction constant, G, because that's all that ever appears. Okay? And I'm going to assume that there is a V of R between two particles. I'm going to approximate that as G times the three-dimensional delta function of R. So the two particles interact only when they hit each other, and this is a short-range interaction. And for this purposes, we never need to worry about the scattering length. We just use the G. Now, the basic Hamiltonian, well, H is sum on K prime, AK adjoint AK times epsilon K0. This is the kinetic energy. This is just h bar squared K squared over twice the mass. And this only includes non-condensate states because the epsilon vanishes if K is equal to 0. But then we have the interaction, and with this potential, this is G over twice the volume. And now you get a sum over K, P, and Q. You can write this in all different ways, but let me just be consistent. So I get A, K plus Q adjoint, A, P minus Q adjoint, A, P, A, K. And this conserves momentum because the sum of these is equal to the sum of these. And you only have three variables because the total momentum is conserved. Okay? Now, Bogoliubov's wonderful idea is that at 0 temperature, in an ideal gas, all the particles have 0 momentum. And so the idea is that if G is very, very small, you ought to be able to do some way of thinking about that it's not very different from the ideal gas case. And so what you assume is the number of particles in the condensate is very, very large for small g, and in principle, if g goes to 0, this should equal n. So we say that n naught over n is a finite number. Okay, and it says that's the macroscopic occupation, and at 0 temperature in an ideal Bose gas, all the particles are in the condensate. The idea that in a weakly interacting Bose gas with repulsive interactions, most of the particles are in the condensate. Okay? And in general, these operators obey the bosonic commutation relations. Aj, Ak adjoint is delta Jk. And for all the particles, except the 0 momentum states, these are just normal boson operators. But for the 0 momentum state, A0, because the commutator of those is 1, but the average occupation, A naught, is of order the square root of n0, you go to a classical picture, the way you do a laser physics, and you say that you treat the operator for the 0 momentum state as a classical field. It's still a quantum problem, but you ignore its commutation properties. Okay? And so we can now look at the number of ways we can make all of these various zeros. In one term, there's a term where all of them are 0. So K and P and Q can all be 0. In that case, we get G over 2V n0 squared, right? And then now, can you have 3 of them n0? What happens if you have 3 n0s? You violate momentum conservation. So you can't have 3 n0s. So the next term is 2 n0s, 1 n0. Well, the next term is to have 2 factors of the square root of n0. This is all 4 factors. And there are 6 different ways. If you have four objects and you want to take 2 of them out of a box, there's 6 different ways you can do it. I'm not going to write it down. It's pretty straightforward to write it down. Well, let me do it just because it's helpful. So if you write this down, you find calling this interaction, H interaction, is 1/2 G n0 squared over V plus G n0 over V 2V sum on K prime. You get 2 A K dagger A K plus A minus K dagger A minus K plus A K dagger A minus K dagger plus A K A minus K. Okay? Now, this is a little strange, and there's a trick that allows you to do this in a way that makes sense, because we assume that n is equal to n0 plus the occupation of all the non-condensed states, AK dagger AK. We can eliminate n0 by writing it n, which is the conserved number, minus this. You just do the algebra. And because this comes in squared, you have to write n0 is this minus this squared, and you keep only the leading correction here, which gives you an extra factor of 2. And at the end of the day, you get a very simple answer, and this is the thing I'm going to work with. So at the end of the day, you get slightly different factors, and it's just this, as I say, a kind of a trick, but it's worth writing it down because it's in our many body book. It's in most of the books. The Hamiltonian is now, and this is what we're going to work with, 1/2 VGN squared. And now I'm dealing with the real n, the total number density, not the condensate density. And this is the thing that's conserved, plus 1/2 sum on K prime. And now you've got a whole bunch of terms. You get epsilon K0, which is the kinetic energy, plus ng. And now you get a k dagger a k plus a minus k dagger a minus k plus, and this is the interesting term, ng a k dagger a minus k dagger plus a k a minus k. Okay. And these look like just a normal conventional Hamiltonian because this is the number of particles with momentum k. But here you get something that's off diagonal. This creates a particle with k and creates a particle with minus k. This destroys a particle with k and destroys a particle with minus k. So these numbers here, these terms here don't conserve particle number. And one way to solve this is to put in a chemical potential and grind it all through. And that works, but it's lengthy. And the trick of going to replacing n0 here by n is the thing that now we can do this directly. So the problem is if you try to use perturbation theory, everything goes crazy. And we'll see at the end that the answer is non-analytic, so there's no way you could have gotten it with perturbation theory. And this is, on the other hand, it is a quadratic form. It's an expression in terms of pairs of A operators. And it's a weird quadratic form because of these things that don't preserve particle number. But you can diagonalize this exactly because it's just a quadratic. It's just like a weird harmonic oscillator problem. You can always diagonalize a quadratic Hamiltonian. And so Bogoliubov wrote down, he said, let's write AK in terms of new operators, UK alpha k minus VK alpha minus k dagger, and AK dagger is UK alpha k dagger minus VK alpha minus k. And you notice this destroys a particle with momentum k. Either you destroy a quasi-particle with momentum minus k, or with momentum k, or you create a quasi-particle with momentum minus k. So this is specifically set up with those signs to conserve momentum. Okay? Now this is very strange, but we know that if you have a canonical transformation, the commutation relations have to be preserved. And so what this means is, in terms of these new operators, we have to have alpha j, alpha k dagger has got to be delta jk. And so if you assume this is true and you use the commutation relations for these, what you find is that uk squared minus vk squared is equal to 1. So the condition that this be a canonical transformation is that these behaviors be preserved. Now, in general, you can take u and v as real in simple cases, although there are certainly examples where you can't. Now, this is lengthy. You substitute these in here, and you get a whole bunch of terms. So you substitute, and what you get is constant or non-operator terms. You get those. You get terms that look like sum on k, alpha k dagger, alpha k, plus alpha minus k dagger, alpha minus k. And then you get terms which are still off diagonal, sum on k prime, alpha k dagger, alpha minus k dagger, plus alpha k, alpha minus k. Okay? And we have one constraint on u and v, but we don't know what they are yet. And what we do is choose the u's and the v's to say, make this term have zero coefficient. So if you choose the u's and v's properly, you eliminate the off-diagonal terms expressed in these new quasi-particle operators. It's just algebra. And what you find is that vk squared is equal to uk squared minus, that obviously satisfies this relation, but it's equal to 1/2 epsilon k 0 plus Ng divided by what I'll call E sub k minus 1. And UK has this with a plus 1. So they have a nice simple symmetry. But now I need to tell you EK comes out of this result, and it's just the square root of epsilon k0 plus Ng squared minus Ng squared. Now, if k goes to 0, this factor goes to 0, and these obviously cancel. So this will be the energy spectrum of the Bogusław quasiparticles, and it vanishes at k equals 0 by inspection. And you can work this out, or you can write this as the square root of 2 epsilon k0 Ng plus epsilon k0 squared. So at large wave numbers, at large energy, this term dominates, and EK just goes over to a free particle spectrum. On the other hand, when this is small, this term is negligible. Epsilon k goes as k squared, and you have a square root, so this has a linear dispersion relation. And so if you plot what this looks like, it's linear, and then it rolls over to quadratic as a function of k. And this k rollover occurs when what's called psi to the minus 1. And I'll talk about that in a minute. But let me just talk about some interesting quantities here first. When you do this transformation, you get h is some constant terms plus, and this is the important point, sum on k prime, 1/2 ek alpha k dagger alpha k plus alpha minus k dagger alpha minus k. So you can interpret, or you can just write it with this without this factor and omit the half. You can interpret epsilon ek as the energy associated with each quasiparticle. So that's why this is such a remarkable result. And just to write it out in detail, ek is approximately h bar k times the square root of Ng over m for k goes to 0. And it goes like h bar squared k squared over 2m for k goes to infinity. And you get a crossover between these two regimes when epsilon k0 is of order Ng, which is h bar squared k squared over 2m is of order Ng. And if you define what's called psi as h bar over the square root of, well, let me write it out this way. It makes it a little more intuitive. H bar squared over 2m psi squared. This obviously has the dimensions of energy. You set that equal to Ng. Then psi squared is h bar squared over 2m Ng. And so this transition occurs when k psi squared is of order 1. That's the easiest way of seeing it. And if you write this in terms of the scattering length with a 4 pi and all that stuff, you write this as 1 over the square root of 8 pi, the number density times the scattering length. And this is interesting because it shows it doesn't make sense to have an attractive scattering length. It doesn't make sense to have an attractive g because the speed of sound here would be imaginary. And so everybody assumed that for a Bose gas in a box, and by analogy in a Bose gas in a trap, that you had to have positive repulsions. Now we'll talk a little bit about that later on. So what we have, not only do we have the quasiparticle spectrum, we have an ideal gas of quasiparticles. So the thermodynamics and all the statistical mechanics of these quasiparticles is trivial because it's just behaving for it's just like an ideal gas of bosons because they obey bosonic commutation relations. Okay, so it's just an ideal gas, and now we can look at some interesting physics. So what is the vacuum for this Hamiltonian? How do you define the vacuum? How do you find the vacuum in any system? You apply all the destruction operators, and if you apply it to the vacuum, they give 0 because you can't take a particle out of the vacuum, right? And so here we define the vacuum. What is the ground state expectation value of particles? AK adjoint AK. Well, we don't yet know what that is because the vacuum is defined in terms of the alphas. So what you do is substitute these two representations in. You have AK acting on this side. This part of it gives you 0 by this relation, but this part of it gives you a finite answer. So this is going to be VK squared times 0 alpha minus k, no, alpha minus k adjoint, because this term gives 0 acting to the right, this term gives 0 acting to the left. And so the answer, and this is just you create one quasi-particle in the vacuum. This is the number of quasi-particles plus 1 in the vacuum, which is just 1. And so this answer is just V squared, VK squared. So VK can be thought of as the VK squared is the occupation of the particular mode K in the quasi-particle vacuum. And now you can immediately calculate the total number of particles that are excited out of the condensate. Because N prime, this is at 0 temperature, equals sum on K VK squared. Okay? Because for each K, this is the occupation, this is the number of quasi-particles with momentum K. And you can write this as an integral. If you go back and check, you'll see that VK squared goes like 1 over K to the 4th as K goes to infinity. So this sum actually converges. It's not obvious, but it does. And you write the sum as an integral.
I just missed this last part. So you're saying that V.
This is the effective ground state.
Yeah. So the ground state of the Bogoliubov quasi-particles. You are showing to us that are the excited states.
There's a finite. The ground state is very complicated. It's non-perturbative because we've done a canonical transformation. Now, just to help understand it, suppose you take the exact ground state of an ideal Bose gas. You put all the n particles in the 0 momentum state. Now you turn on a weak repulsive interaction and ask, what is the perturbed ground state? The first thing that you can do is take 2 particles out of the condensate, let them hit each other, and that creates a pair of particles with plus k and minus k. And if you go on in perturbation theory, you eventually get divergences, but you can understand why the presence of repulsive interactions says that the exact ground state has occupation not only of k equals 0, but all k, but the occupation of all k is very small. And Vk squared is the occupation of a state with momentum k. And the fact that this goes like 1 over k fourth means that this sum is convergent.
Okay, so but that's the number of particles out of the ground state.
Out of the ground, no, out of the condensate.
Out of the condensate.
The condensate, you have to be very careful, because k equals 0 is the condensate, but the true ground state, the non-perturbative ground state is this 0.
So the vacuum of the Bogoliubov quasi-particles is the out particles of the ground state, of the...
Well, the vacuum of the Bogoliubov quasi-particles has n0 particles in k equals 0, and n prime particles in k not equal to 0.
Okay.
And so that's why it's very important to distinguish between the condensate and the superfluid density, because the superfluid density is calculated in a different way. And even in an interacting system, the superfluid density at t equals 0 is equal to the total density. So you've got to be, most people are careless about that. But there's an intellectually important difference.
For helium, that's essential, right?
Yeah, it's
So you
huge.
go to
It's
zero,
huge.
you have a
But I've had arguments,
30% of particles.
very intelligent people, I've had long arguments about this with, so you never know. Now, the nicest way of writing this is to write n prime over n, or this is n minus n0 over n. And you can do this integral. It takes some work, but the answer is nice and simple. And the answer is 8 over 3 na cubed over pi to the 1/2. Now, Bogoliubov didn't do this calculation. He could have. He wrote down this expression. And he said it's manifestly non-negative. It's manifestly positive. And so there is a quantum depletion of the condensate caused by the repulsive interactions. But he didn't. Here I've gone using this G is 4 pi a h bar squared. And now there's just a factor of m because the reduced mass has a factor of a half in it. And so I'm using the S-wave scattering length here. And the most interesting feature here is this goes like a to the 3/2. Now, you can never, never, never in perturbation theory obtain an a to the 3/2 as an analytic expression because it has a branch point. The radius of convergence is 0. And so the reason this works is it's a canonical transformation which is non-perturbative. And it's the non-perturbative character here that makes this so elegant. Now, if you go back, you probably won't because it's lengthy and hard, but Li, Huang, and Yang they must have written 10 papers on this subject in the 1956-57. And they did perturbation theory. They got divergent answers. And Yang, they're very clever people, obviously. And Yang and Li, well, I don't know who, they came up with a way of summing the most divergent singular terms and ignore the others. And if you just hold your nose and shut your eyes and sum the worst divergent terms, they actually got this answer in this form. But as I say, Bogoliubov could have written it down. All he needed to do was write this down and do this integral, which you can do. It takes about a page of doing. I like to do it by integration by parts. But it's not trivial, but it's not that hard. Now, what is really hard, and this is what I think Li, Yang, and Huang get credit for particularly, is the calculation of the ground state energy. And let's see, I guess I can erase all this. When I wrote down the energy, the Hamiltonian, I wrote down constant plus the sum on k, ek, alpha k adjoint alpha k. But this constant is not a simple thing to evaluate. And the leading term is this 1/2 g n squared over v. And if you express this in terms of the scattering length, this term becomes, let me write it down right, you can just, it's immediate. You get 2 pi a h bar squared n over m. This is, and then there's a factor of capital N. The total energy is proportional to n, so you write it as E over n normally. But you get this factor, and this comes from just the term that's trivial. The next term is also divergent. And you can understand the divergence in various ways. It's because you've approximated what is really a non-singular potential by a delta function. And you're trying to do perturbation theory in delta functions, which sounds bad. It is bad. There are tricks, and the famous result, which is analogous to this result, but is much harder to derive, is that the ground state energy over n is this 2 pi A h bar squared over little n over m. And now you get 1, which is the term that you get trivially from here, and you get this famous term 128 over 15 na cubed over pi to the 1/2 plus dot, dot, dot. And this is what's called the Li-Huang-Yang correction. But to do this, you have to play games with your perturbation theory because there are various things that go wrong. I mean, this answer everybody believes in, and Li, Huang, and Yang got this answer, again, by summing most divergent terms. And what gets particularly hard if you want to calculate things like this in a trap is how you do the renormalization, how you do the cutoff in a consistent way in a trap because you don't have translational invariance. And again, you see this non-analyticity, a to the 3/2. If you do the perturbation theory for an electron gas, what you end up with is log of E squared. So that's another non-analyticity because the log has a branch point at the origin and there's no finite radius of convergence. And finally, the worst of all is the BCS theory that goes like e to the minus 1 over the coupling constant. This is not only not a branch point, it's an essential singularity. And so all these three sort of pillars of many-body physics, the electron gas, the dilute Bose gas, and the BCS theory all involve very non-trivial ways of dealing with problems which are intrinsically non-perturbative because the perturbation theory doesn't even begin to make sense. And the BCS is the worst of all. Ironically, it turns out that there is a very elegant, BCS didn't do it this way, but there's a very elegant canonical transformation. If Bogoliubov had understood about the attractive interactions, he could have written down the BCS theory 10 years before, because the BCS theory was 1956-57, and this was 1947. And so the only difference is in the BCS theory, you're dealing with fermions, and so you get U squared plus V squared is equal to 1 because things have to anti-commute instead of commute. But the formalism, you end up with very similar formalism, and you do a canonical transformation, you eliminate the off-diagonal parts by choosing U's and V's correctly, and you get answers which are not very different from this, but it's just the energy thing that goes in here is different. You get the BCS energy instead of the Bogoliubov energy. But the parallel is pretty amazing. So, and I mean, I'm told Bogoliubov sort of kept hitting himself. I wish I'd thought of, why didn't I think of that? Why didn't I think of it? But it was the physics. Bardeen had spent 20 years of his life mulling over the BCS theory, mulling over superconductivity, and he'd been working on it for forever. The moment he finished his transistors, inventing the transistor, he went back to superconductivity. In 1954 or 55, he'd written a very long review article where a lot of the structure of the BCS theory was there. The essential thing was missing is what was the structure of what led to the attraction and what was the structure of the Cooper pairs. And it was Cooper's idea, the Cooper pair. Then Bardeen immediately said, oh, that's the missing piece, and now I have all the pieces, and wrote this amazing paper where they did all the electrodynamics and the thermodynamics. And it's because he'd already done the electrodynamics for this review article that he understood it. So it's a fascinating history.
Just like with the, in a very hand wave type, what is the n prime over n for a non-box potential? So if I have any, like a parabolic potential, the scaling with A will be different, right? But there is no, you know what I'm saying?
Yeah, I'm not. It certainly has been worked out. I don't know. I don't remember. I mean, the first problem, which I'm going to spend most of next time on, is you don't even have the zero approximation in a trap because you don't have the wave functions. When you have, here you have a box, you have periodic boundary conditions, so you know the wave functions is plane waves. And so you use this Bogoliubov theory to add the effect of the potential. But in a trap, you have three lengths. You have the interparticle spacing, if you like. You have the size of the trap, and you have the scattering length. And so once you get 3 lengths, that's why you have to go to the Gross-Pedievsky equation. You get 3 terms. You get the kinetic energy, the trap energy, and the interaction energy. And it's in different regimes, you have to balance pairs of those against each other. And when all 3 of them are important, the ground state, the structure of the ground state, there isn't a simple description quite like this because the properties of the ground state depend on this, well, you know all this, the ratio, the number n a over d. And if a over d is like 10 to the minus 3, but n can be 10 to the 6, so this number can vary between 10 to the minus 3 and 10 to the 3 depending on the number of atoms in the system. And so the ground state energy depends crucially on this. And so there isn't, here we're just talking about this term. So just to get the ground state energy, the Gross-Pedievsky equation is basically just determining this term. And then to get these terms, you have to start, people have worked this out, I just don't remember. But then you have to start looking at the quasi-particle spectrum, which are the Bogey-Uboff equations, but in a trap, they're much more complicated differential equations. Because you can write a canonical transformation formally in terms of the solutions of the Bogey-Uboff equations, but it's a big numerical problem to solve them.
But you can apply always this approximation to the trap, right? There is no condition where you
I think you can always apply at low enough temperature. Here this is all zero temperature.
Zero temperature.
Yeah, I think that's always a good approximation. Okay, I will stop here. Next time I want to talk about the density fluctuations, which is interesting in the Bogey-Uboff picture. And from that you can calculate this S of Q and omega, and then I'll talk about the trap afterwards. Okay?